In this video, we'll be discussing the intersection of cryptography and machine learning. It's actually not too surprising that cryptography and machine learning can be viewed as sister fields with many intersections, since they share key central concepts. In cryptography, we typically want to break a system by finding the secret key, where the system is known. As such, the decryption function comes from a family of functions. This family of functions is known since we know the system. Our goal is to identify which function is being used. We also typically have ciphertexts and their matching plaintext to help us with our analysis. Therefore, the problem can be described as learning an unknown function from input-output data and previous knowledge of a class of functions.
The idea of the secret key in cryptography corresponds to the target function in ML theory. In addition, the key space in cryptography corresponds to the class of possible target functions in ML theory. For encryption purposes, these functions might also be efficiently invertible, whereas there is no such requirement for functions in a machine learning context.
There are some important distinctions to make. In cryptography, it's common to assume that we know the size of the unknown key, since the system is known to us. However, current research in machine learning theory assumes that the complexity or size of the target hypothesis is not known beforehand. For example, we might want to try to fit a polynomial function to a set of data points, but the degree or size of the true polynomial that the data might have come from is not known in advance.
The primary impact of cryptography on machine learning theory is a negative one, showing that certain problems are computationally intractable, meaning that there is no efficient algorithm to solve them. The result from Kerman's and Valiant's paper show that if a learning algorithm could learn any of the classes of functions that we described earlier, meaning that they could predict with significantly greater than 1/2 probability the classification of new data points, then the learning algorithm could be used to break the cryptographic problems assumed to be NP-hard.
Since most of the negative results in learning theory already depend on cryptographic assumptions, there has been relatively no impact of negative results in learning theory on the development of cryptographic schemes. Many of the positive results in learning theory are normally independent of cryptographic assumptions and could in principle be applied to cryptanalysis. We will outline some possibilities, but their proof and applications are still left as open problems.
There have been successful applications of continuous optimization techniques, such as gradient descent and backpropagation, to discrete learning problems. Similar techniques can also be used for cryptoanalytic problems. Another area where crypto and ML relate is that of data compression. It has been shown that pack learning and data compression are essentially equivalent ideas. The security of an encryption scheme is improved by compressing the message before encrypting it, so learning theory may help cryptographers by allowing for even more effective compression algorithms.
I think it's for me it's the opposite sides of the same coin. That if you get a function, you want functions which you get a black box say with the behavior.
Yeah.
If it's either it's easy to figure out the function from the behavior, or it's hard. So in cryptography, you're looking for a case when it's hard to figure out what's inside the black box from the behavior.
Yeah.
In learning, you're looking for where it's easy. So it's you could say it's the easy and hard part of the same phenomenon. Well, the people in any field of science, every field of science has kind of a birth and a middle age, and then it gets less interesting eventually. So probably each stage of a field probably maybe needs different skills. It looks different for researchers. At the beginning, people just don't know what they're talking about. They're just trying to understand what's going on. And towards the end, it gets very technical. You have to read 1,000 papers. So I think it's probably mainly different skills now from those days. But I think it's hard to say what's easier and what's harder.
And where would you say computer science is in that lifespan?
Great question. Well, no, I think it's okay. So since I was there in very early days in computer science, where we worried a lot about whether we knew we were at the beginning, but you didn't know whether it was going to be big or small.
Yeah,
small. No, but I think computer science is still very big and growing. So it's not. I think it's still expanding, I think. So it's still fairly useful, I think. Some fields, like if you mentioned cryptography, so I think most computer scientists were thinking about cryptography, they thought it was something done by secret agencies, and that they knew all about it. So this Diffie-Hellman paper came out and drew people's attention, and yes, maybe they did questions for computer scientists, and then the reverse Adelman paper came out. So that was a case when people in computer science just didn't think cryptography was a suitable or could be studied by this community. In that case, because they thought that there were some experts who already were miles ahead. But other fields like in complexity, so when certainly when NP completeness came out, that was totally revolutionary. Because I think the obvious advice is always to follow something which excites you. Know? Because if you're not excited by it, then you just won't put in the effort. I don't know. I mean, so I started with complexity theory. I think it's still pretty exciting, and we still don't know very much. And generally, the machine learning AI field, I think, is still a great area because